This is my project on using fugacity to determine the degree of risk of pesticides as an environmental hazard. I say degree of risk because essentially degree of risk will be modeled by concentration of the pesticide, because that's how fugacity is incorporated in the study. It's to calculate a concentration of the pesticide, and basically higher concentrations will yield more of a risk, right, to humans or plants in the environment. So I say degree of risk. Applications of fugacity in real life. So fugacity allows us to understand the movement and behavior of molecules under varying conditions of temperature, pressure, and concentration. It allows us to model the behavior of these various chemical substances under these varying conditions, though, without actually having to create them in the real world environment. Um, so that is how it kind of acts as a proxy or a means for us to calculate um, their impact and the way they behave in the real world. In this specific study, done on the environmental and public health hazard posed by pesticides, specifically in this study, the pesticide in question is flopyram. Fugacity was used to better understand the complex chemical interactions of flopyram within the soil and sediment specifically, and thus the risks they pose to individuals who are exposed to these chemicals. The next slide, I will go into how next two slides, I will go into how this is done. So the background of the study was that um, it's not on the slide here, but essentially the main goal of the study is to understand how using different soils and sediments can affect the concentration of the the contaminant, flopyram, in the environment or in the soil, in the sediment. And based off that, you can understand, hey, a higher concentration of the contaminant is going to yield more of a risk to workers that are working in the field all day or working around these crops, or even the plants. Maybe the plants have a higher toleration for flopyram and some have a lower toleration. So the ones that have a lower toleration cannot experience these high concentrations of the contaminant. So understanding what kind of soil and sediment combinations yield these higher concentrations is important because it allows us farmers and people to make strategic decisions on what kind of soil and sediment to use. So now that that main purpose is out of the way, um, we obviously understand that pesticides are used primarily in the agricultural sector and they pose toxicity risks to humans, plants, and animals. And in terms of calculations, we can, again, calculate these concentrations of the pesticide using fugacity, specifically a level one fugacity model. A level one fugacity model assumes phase equilibrium, which means that the fugacity across each phase is constant. So um, there's a molecular structure of flopyram down the bottom right. But on this next slide, here, this third equation in the bulleted equations is one of the equations that we learned this year, where the fugacity in phase A is equal to the fugacity in phase B when we have phase equilibrium. Primarily, we focus on vapor-liquid equilibrium in class, but in this case, we have multiple different phases or compartments that the study broke the environment down into. Um, as we talk about on the slide here, the seven major compartments they broke it down into was air, aerosol, water, suspended sediments, fish, soil, and sediment. That should be suspended solids, not sediment. Um, but the equilibrium that was assumed between each phase meant that the fugacity is constant across each phase, right? So the fugacity of um, flowpyram in air is the same as it in water, is the same as it is in soil and suspended solids, sediment. Um, the image on the right is not based off this research study, but it is an example of how a level one fugacity calculation can be made. There you see the different phases, air, soil, water, etc. And then a uniform fugacity value, which is calculated because it's the same across each phase, right? The calculations here or in the study were made based off the equations here. So where M is the total moles of the contaminant, C is the concentration, F is the fugacity, V is the volume, and Z is the fugacity capacity, which is a value based on various chemical properties like temperature, density, as you'll see on the next slide. And essentially, yes, we use these equations. We see that total moles is equal to our concentration times our volume in a certain phase, or the sum of our concentration and our volume in each phase. Um, Concentration can be broken down into fugacity times the Z value. We can sub that in to say our total or our moles in a certain compartment is equal to our Z value of that compartment, our fugacity of that compartment, or if the contaminant in that compartment times the volume of that compartment. Then we can isolate fugacity, that F value, and have it equal to our total moles over the summation of our Z value times our volume. Um, here's the example problem right here. We've been given our total moles by the study there listed on the paper. I've written down the volumes also of each compartment given by the study. And the Z value here, I've also calculated based off a bit more tedious process because the Z values are based off different equations. So right here, it's hard to see, but for the Z value of aerosol, is dependent on a value that is based on the melting point temperature of the pesticide in question, the contaminant, which is flowpyram. Then for soil and sediment, you can see that it's based on the densities as mentioned earlier. So again, a different density will give you a different Z value, which then, because going back to our fugacity equation, is going to give you a different fugacity value. We can then use that fugacity to plug it back into our second equation right here. Right here at the bottom of the page, you see once we have a fugacity, we can multiply that by the Z value of a particular compartment. So for soil, we can calculate it, calculate the concentration of flowpyram in the soil. And we compare these concentration values, as the study did, to understand which soil sediment combinations with different densities produce certain Z values, produce certain fugacity values, and thus produce certain concentration values, and which ones are higher, which ones are lower, and then how to optimize for whatever the goal is in the company or for the farmer in the agricultural sector. So that's just an example of how fugacity can be used to connect to real world topics.